Welcome to Ask and Learn.
In this problem, we're going to talk about conservation of energy. So we need to remember that the initial kinetic energy of a system plus the initial potential energy is equal to the final kinetic energy plus the final potential energy if the mechanical energy is conserved. That is, if the forces that are acting on the system are conservative. In particular, for our exercise, we need to remember that the gravitational potential energy is equal to minus Newton's gravitational constant times the mass of one of the objects times the mass of the other one divided by the distance between the two objects. And besides, we're also going to need the concept of work. So the work exerted on an object is equal to the integral of the force over distance from the point where the force starts being applied to the point where the force stops being applied. And it also can be written as the average force times the distance delta x. So the average force, and the average force is defined as 1 over delta x times LF uh, dx x0 to x, where delta x is 0, x minus x0, I'm sorry. Okay, so now we can calculate what the exercise asks us. So basically we have a meteor that is moving with an initial speed vi of 90 meters per second with a mass of 575 kilograms at a height from the surface of the earth of 850 kilometers. And the meteor hits the earth, hits the sand of the earth, and it is completely stopped by the sand after traveling a distance of 3.25 meters in the sand. And our goal in question A is to find what is the final speed of the meteor, vi. And here I'm just going to use conservation of energy. So I have that m vi squared over 2, this is the initial kinetic energy, minus g m times the mass of the meteor. Here capital M is the mass of the Earth, divided by the radius of the Earth plus the distance between the surface of the Earth and the meteor. This is equal to m Vf squared over 2 minus gm m divided by the radius of the Earth. Okay, so the m's cancel out, and our goal is to find Vf, so that's what I'm going to do. So Vf squared over 2 is Vi squared over 2 plus G capital M times 1 over R minus 1 over R plus H. So what we have is that Vf is equal to the square root of Vi squared plus 2gm times 1 over R minus 1 over R plus H. And a couple of things we need to remember. First, that the radius of the Earth, I'm even going to write it down here, the radius of the Earth is 6.38 times 10 to the 6th meters, while the mass of the Earth is 5.98 times 10 to the 24 kilograms. And finally, the gravitational constant is 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. So Vf is equal to the initial speed, which is 90 meters per second, squared plus 2 times 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared times 1 over the radius of the Earth, that's 6.38, times 10 to the 6 meters, minus 1 over the radius, plus, actually, I think it would be better if I just wrote this in the next line so that I don't have to shrink my number so much. So we have minus 1 over 6.38 times 10 to the 6th meters plus h, and h is of 850 kilometers, so it's 8.5 times 10 to the fifth meters. Okay, I'm sorry for having written this in two lines. So VF is equal to 3,835 meters per second. Then in question B, our goal is to calculate what is the work exerted by the sand over the meteor in order to completely force it to a halt. So the work is going to be equal to the variation in kinetic energy of the meteor. Notice that the initial kinetic energy is equal to the initial kinetic energy is equal to mv squared over 2, while the final kinetic energy is just 0, since the instead of calling ki, I'm going to call it just k, and the final kinetic energy k prime is 0 joules, since the object is at rest. So the work done is equal to the kinetic energy that was lost. Actually, there is a minus sign here. So the kinetic energy that was lost is just mv squared over 2. The mass is equal to 575 kilograms. V is 3,835 meters per second squared divided by 2. So W is equal to 4.23 times 10 to the 9th joules. This is the work done over the meteor. In question C, we have to calculate the average force that the sand exerted over the meteor. And if you remember, the average force times the distance is equal to the work. We know that the distance along which the force was applied is just 3.25 meters. So F bar is W divided by D, so that's 4.23 times 10 to the 9 joules divided by 3.25 meters. And this is equal to 1.3 times 10 to the 9th newtons. Then in question D, I'm going to calculate what is the thermal energy that was lost. Basically, what is the thermal energy that's produced? I'm sorry. So the thermal energy, I'm going to call it Q, assuming that the all the kinetic energy of the meteor is converted to thermal energy, then Q is equal to the work that the sand did over the meteor, and that is equal to 4.23 times 10 to the 9 joules. And this concludes our exercise.